Okay, so this is going to be a little bit more of a different type of talk. Has anybody in here had geophysics? Yeah.
We're going to be working with you.
Yeah, okay. So we're going to be talking about geophysics, development of a conceptual groundwater model. So I'm not sure how much you talked about the geography of the area so far?
Yeah,
But-
yesterday we kind of did some, but not, it's always good for them to hear it like 20 times.
Okay. So this is kind of the general area we'll be working in right here. And we've been working more on the whole bunch fracture zone as well. So up to date, you'll be staying in Puerto Morelos here. And we worked a lot along this Ruta de los Cenotes in this area. And did you show them this map yet?
Yes.
Okay. It's quite a mess. So we've tried to focus again on this area here with water flow going in different directions. So it's kind of a groundwater divide between the Hobart fracture zone and then the water that goes toward the coast here. So we sort of focused on that in the past. And in this whole area, you've got a freshwater lens, so a limited amount of fresh water. There's an interface here with the salt water. And that's been one of our targets for the geophysics. And you probably already discussed some of these problems. Cancun's public water supply is contaminated. You have a very limited amount of fresh water due to the saltwater freshwater interface. The water table is very close to the surface, so it's susceptible to contamination. And this is what you see, and you'll see this a lot in areas working. This is a karst conduit. Some of them are large, some are small. Actually, I'm going to trim.
Much better.
Yeah. This one, we always stop at this place. You can see garbage in this one. And each year we stop here and we see different garbage, which means that it's flowing down into the groundwater system. And you'll see that's quite a bit. People put trash of all sorts in these sinkholes. One of the things you can't do here is really do surveys in the jungle. This is what it looks like. You'd have to do a lot of chopping, have enough space for a geophysical line. So we work on roads. This is the typical road. You can see our tape laid out here. These roads are mostly along the well field, along the wells. Again, shallow water table. This is a small cenote we worked at a number of years ago. You can see this green water down here. And this is a well that they were fixing. If you look really carefully, you'll see some of the water level right there. So targets for geophysical surveys, preferential flow pathways, just like we saw in large fractures, sinkholes. Water table depth, that's another target. And hopefully we'll see changes in the water table, so be able to tell what direction it's flowing, the water's flowing in. And then saltwater freshwater interface is always a target. So those are our three main geophysical targets. Get some water here. So geophysics. We're going to be doing mostly resistivity this year, a little bit of self or spontaneous potential. So I wanted to go really quickly through some of the techniques and show us a bunch of pictures from the last REU. So resistivity, you probably are all familiar with Ohm's law. V equals IR physics. We're actually not looking at resistance, we're looking at resistivity, which would be the symbol rho to represent, because it's what's called an intrinsic rock or soil property. That means it doesn't depend on how it's measured. Resistance does. So in this example, let's say this is a rock core, length L, cross-sectional area A. The resistance is resistivity times L over A. But the resistivity just depends on things like porosity, rock type, degree of saturation, what kind of pore water you've got, metallic minerals, things like that. So with our standard array, we call this a resistivity array. You've got an A and B electrode. Those are the current electrodes. You can see it's hooked up to a battery here and a current meter. And then you've got your potential measuring electrodes, M and N here. So the current flows from A to B, positive, this is negative. There's a battery hooked up here, just like literally used car batteries. And then these dashed circles are equal potential lines. So what you want to do is measure the potential difference between M and N in volts. So it's different configurations. This one's called the winner array, where they're all equally spaced. That would be up here. There's another configuration where your M and N are very close together. Your A and B are further apart. That's called the Schlumberger. And then there's another one where your current electrodes are over here, and your potential measuring electrodes are here. It's called the dipole-dipole. Okay. So we'll be using all three of those types of arrays. So this is some pictures of equipment. This is a resistivity meter. Now this one's got the battery inside of it. We won't be using exactly this unit. We'll be using a very similar unit. It's powered by an external battery. If you look really carefully, you'll see an electrode up here. There's our electrodes right there. So they're stainless steel stakes. And because we're usually working on rock, you have to pound them very hard to get them in. Then we'll pour salt water on them to get good contact with the ground. Here's a recording book. Write down the numbers, and then these are the cables which get hooked into these banana plugs here. These cables are quite long. We have a couple, I think they go up to 200-300 meters, because we have to have very long lines. That's why we work on the roads. So this is one area that we've done a lot of work at. It's called the South Wellfield Road. It's a very nice area to work because you've got this big space here. If you look really carefully, you can see a well over here. So we've done a lot of work at this location. And this is what you record. This is a resistivity sounding, the well 49A. So you record you increase your spacing of all your electrodes, and then you record your apparent resistivity. Measure. Okay. And that, as you can see, it starts low, goes up high, and then goes back down again. So then you interpret that with a layered model. So you get a chance to do that because you're doing the geophysics work. We have a program that we use to do that. So it goes from this to this. So we interpret the top as a crushed, rubbly zone, kind of a weathered zone. Massive limestone underneath that, and then there's the water table right there. In this case, it's about S times 10, so that's 10 meters of that. You can see the resistivity drops significantly when you hit the water table. So you're doing all this on the surface, there's no wells involved. But the system senses when the resistivity goes up and when it goes down. So it's kind of neat, it actually works. And you can see like below the surface with it by just doing surface measurements. So that's actually one of the few outcrops in the area. This is in the quarry. And you can see that there's that rubbly zone right there, the massive limestone. And then actually you see a little water down here at the bottom. That's the water table.
Question.
Mm-hmm.
So what kind of properties, so you said this is a quarry, what kind of properties are going through under and they're affecting some of this?
So we would be like on top of here,
Yeah.
trying to interpret what's going on. You can see some big fractures, kind of a cave right there as well. So,
These are man-made quarries, right?
yeah, this one you won't be able to get into, but actually it's the only outcrop I've seen, like a vertical section like this in the whole area.
Yeah, so they're mining the limestone there, so what they do is they mine it for road aggregate, and they actually send it around the whole Caribbean region. And so, and then Calica, we'll be driving right by it, when we go to Rio Secreto, it'll be right to our,
Yeah, you go right by.
south of us. We can't go in there anymore, but what they're eventually gonna do is they're taking the rock out down to where that water table is and just going a little bit below that. And then they're gonna make it into these large freshwater lakes where they're gonna have like resorts and people living on the edges of it. And then they're gonna have these lakes, so that's the eventual part of where this is going. But the rock that's here is the same everywhere, as I showed you that flat, it's the same material everywhere. They're mining it here just because there's a port right there.
Is there like an effect because of this concentration of material going down there? Too much going inside the water? I don't know, you know.
I'm trying to, like, what do you mean by,
Like, you know, too much salt in the water. Is it going down into the waterways or?
oh, this doesn't hit the salt water. They stop before they hit the salt water. Yeah, so this only goes into the fresh water, they don't go into the saltwater interface, so it's not, so, and this is interior, it's not right on the coast, so it's not like right on the beach. So we're in like about at least a kilometer or two inside of the area, so, none of it's getting inside of the ocean.
You can sort of see if you dispose something up here on the top, it's going to go right down these fractures, all the way down to the water table. So here's something else we did. This, if you spread your electrodes far enough apart, you're actually going to see the saltwater freshwater interface. So here, the spacing is on this one 100 meters, which means we have actually a 200-meter long line. And you see the water table here, where you get the first drop, then you get a huge drop when you detect the saltwater freshwater interface. So we've seen that a few times. We were hoping to see that again this year in different locations. So it gives an idea of changes in the saltwater freshwater interface. Basically, that gets deeper as you get away from the coast.
And and we have to get the exact elevation of the ground,
Yeah.
so that we can then, and somebody asked about groundwater flow, so we can figure out where that table is and that freshwater, saltwater interface is with the actual elevation is this. As you can see, depth on the axis there, but if we don't know what the elevation of the top is, then we can't compare and contrast.
Okay.
And so that's one of the things that we're doing this year, is getting some really good GPS in on those, so we get good elevation.
There's some other things you can do with resistivity as well. This is the system actually we'll be using when we're down there. It's called the Sting system. And it's got another box with it that turns electrodes on and off in different configurations. Usually the dipole we showed earlier. So what you do here is you set up a whole line of electrodes. You hook them to the box, and it's computer controlled, which means you don't have to keep moving the electrodes. Collects a large amount of data fairly quickly, and you produce what's called a 2D section. So this is one which very nicely shows a fracture zone. These are high resistivity areas. Fracture zone is a low resistivity area. It probably could be because it contains moisture or clay. So these are very appealing diagrams because it looks like a two-dimensional image compared to looking at a graph.
So where on the graph, sorry, will it show us like the water flowing?
That would be the lower resistivity area, so probably this might be the saturated area. The blue is about 114 millimeters, so that would be basically we see the blue would be where the water is. And then below that, you've got some very massive rock that's very high resistivity. So presumably, this is the water level that's flowing down this fracture, but not really penetrating into these rocks here. So we'll be doing several of those lines as well. Now self-potential or spontaneous potential is a little bit different. It's where you just measure with the measuring electrodes, moving them around in different configurations. The idea here is that if you have moving water going down into a fracture, it changes that potential. It's one of the things that happens when you do that. The faster the water moves, the more water is, the larger the change you'll see. And this is a survey we did a number of years ago. And here you can see part of the cenote over here. So you set up these are special types of electrodes. They have ceramic tips on them. You fill it with copper sulfate solution. And then you can see, if you look very carefully back here, you'll see the instrument we use for the recording. So these are just done with 2 electrodes. There's one there. Usually you keep one stationary and then you move the other one. This is one of our former REU students. This area was unusual because they had cleared it. Normally this would be the jungle. They were trying to develop the cenote. It didn't really go well. It was abandoned when we got there. But it gave us the chance to actually see, and if you go back in here, you'll actually see sinkholes and all sorts of things that normally you wouldn't see.
And one of the reasons it got abandoned was, so what happens, just, and I didn't really talk too much about this, is people buy property down there, and if there's a cenote on it, oh yay, we can make a lot of money. Well, sometimes they may have one of those really tiny holes that Phil showed, where it's just like a little small spot, and they're like, well, what happens if we blow, we mine the rock off the top, we blow that up, and we'll make a cenote, so we can have a tourist thing. Well, those are hydrologically not connected to the groundwater flow. So the ones that are crystal clear, they're the beautiful ones that all the people go touristing, they're just beautiful. The ones that are these, because they're not part of the whole local hydro and the groundwater flow, because they were man-made, they start to get a lot of algae into them, they get really disgusting and gross. And no one wants to swim in them because the water is not the same. And so one of the cool things we've been doing is, Phil's can use these areas to get in there, but then we can also do the geochemistry on the area, so we can linking those two together. So we will see some of these. So some of these cenotes are better than others.
Yeah, you can see all the blasted rock from excavation.
No, I know Ken, when in his presentation earlier, showed us that map where there's like a region that we don't really know how the water is flowing. So will there be any opportunity for us to do surveying in that area? If there's a road that we can look into?
Yeah, that's what we've been trying to do actually, is go to different locations, mostly along that ruta to those cenotes, finding different locations. That's what this location was actually. Now this is closed now, so we can't go to that site, but there were other sites. And then you try to link that with the water levels that you actually measure in the cenotes. And in the well field also, we had water levels in some of the wells that we could measure. So you kind of combine the geophysics with the hydrogeology, with all your data, to get a sort of integrated picture. By the way, this is the type of clothing you might want to wear down there.
Oh, yeah.
It actually keeps you cooler than putting a short sleeve shirt on. And everybody needs a big hat. So.
If you don't have a big hat, you should buy some.
And boots, because you can, walking on this, you can see that's going to tear up tennis shoes pretty fast. So this is an example of one SP profile where we actually, here's SP in millivolts, and you see a big change right here. So that was a fracture. And here's a sort of a 2D, 3D SP image we collected on our last REU along the road, and we plotted it up here. You can see this area, there's actually a sinkhole right here. This area looks like there's water flowing toward it. So that was kind of interesting to see. Okay, so we're not going to do these methods, but I just wanted to show you what we've done in the past. We've done time domain electromagnetics. That's like the resistivity method, but it uses coils, big loops of wire, instead of pushing electrodes in the ground. It actually goes much faster, and it's a lot less work. But we couldn't acquire this equipment this year, so we won't be doing that method. It's also a very good method for finding the saltwater freshwater interface. There's an example of some data. So you have a sounding curve just like before, and then you invert it. And there's a water table, freshwater, saltwater interface. In this location, it was about 30, almost 40 meters deep.
Which one's more precise?
I like the resistivity, but it's a lot of work because you've got to have a very long line. This actually worked remarkably well there. So I'd say they're about the same. This works better for real deep freshwater, saltwater interfaces because otherwise you have to have a very long resistivity line. The other method that we won't be able to do, and we tried to get some equipment for this, but it wasn't really available, is ground penetrating radar. It's where you send radio waves into the ground and they bounce off interfaces. So it's a very simple technique in the field. You just have a transmitter and a receiver here. The transmitter sends a signal down, bounces off, say the water table or something like that, freshwater, saltwater interface, or rock layers, and then you plot them up as a section. And you can, there's the instrument. We took this down one year. There's a transmitter and a receiver. These are 50 megahertz antennas. So it's sending, well, 50 megahertz is a little bit lower than the FM band, but it's still close to it. We also have 100 megahertz antennas, which are very similar to your FM receiver. So you just march these along a profile line. And there's a former student, Ryan Adams, and that's Rosa there, collecting some data. And again, we're along a well-filled road here. And here's an example of a display. So you have time, and this is very short amounts of time. These are in nanoseconds. And then profile position right here. And this was a really interesting section because we saw a conduit. Actually, this is close to that conduit with the garbage I showed you earlier. And then very near there, we have the zone where there's no signal at all. Well, it's a transparent zone. It's probably a cave below the surface. Because what happens is when the signal hits air, it gets refracted. It goes very fast through the air, so you don't get a reflection there. So this is a really interesting section. So I wanted to show you some pictures from the last art review. Again, people doing field work. Here we are doing a resistivity line. And you can see, if you look really carefully, there's an electrode here. You'll notice there's hammers here. You have to pound these in. It's hard work, especially when it's 95 degrees out, 90% humidity. This is salt water, a bottle of salt water we pour on the electrodes.
How deep do
You have to pound them in, say about 5 centimeters at least. It is hard because you're on solid rock, as you can see here. There are a few places where there's soil, but it's almost always solid rock. So we do a lot of pounding. And there's some more of our students. This is one area where we had some vegetation. So yeah, I definitely would wear long pants, long sleeve shirt, because you'll get into some prickly stuff here. And there's our, that's our two-dimensional system that, and we'll be using this. We could go down there. Again, the yellow box and then the switching box here. And then if you look really carefully, you see a 12-volt battery over here, which powers the whole system. And there it is again. And you can see all the electrodes here and the cables. This one I actually did in Puerto Morelos, right outside. It's called the Science House. We were testing the equipment out here, and actually worked quite well there. So our house is right here in the corner. You can't see it.
You know, they changed that road right there into the massive, like, they're making it into a 4-lane road.
Oh, they
Or
did?
up in front of Rosie's house, all of the palm trees, and we'll have to find a new place like this.
Yeah, actually that might be your house right there. This is a good place to test equipment out, because you need space to do that. You need, there actually was a little soil here, a lot of garbage here too sitting. There's again our battery to power the system. So one other thing we did was, the first time we did this down there was we rotated the whole array around a circle. And again, you need a big space to do that, so we found 2 soccer fields. The purpose of this is to locate fractures. And you get different resistivity in different directions when you orient it with respect to fractures. This was another unit that we actually brought down and used for doing that. I think you got a couple more pictures of that. So this is one of the fields we were working in. I think this was the first place. So there's a midpoint, and then you just rotate this around generally 180 degrees, sometimes the full 360. And you have to have somebody with a compass here to measure the direction. You generally take a measurement every 20 degrees. There's another one. This would be the center point right here. And there's Mel, 2 of our students. This was a really hot day, as I remember. We sent people in to get ice cream, watered. So your final product is going to be a poster. Here's one of our students' posters from last time. And you learn how to do that to present your poster today. Are they going to do the research conference?
We're not gonna be able to, no, they're not doing it in person this summer. But we're gonna do the poster session here on the floor.
Mhm.
So just so you guys know, you guys are going to produce a poster like this, and you can see them up and down the hallways. And what we're gonna do is we're gonna put them all up and down the hallway here, and then invite people to come in and hear you talk about your research. So we're gonna do that on the 13th. They're not doing the group one. The 13th of August, yeah.
So you can see here, he has a map showing location of the surveys. We did a 2D resistivity section that actually shows a nice fracture. And then these are the azimuthal resistivity plots, where you plot out your apparent resistivity versus direction as you rotate. So this one's nice because he has a kind of a nice balance between the amount of pictures and the amount of text. You don't want too much text on your poster. I think that's the last slide here. Oh, one more. So these are some of the results that we got from previous surveys. Again, resistivity soundings, that's where you expand the electrodes around the center point. We're able to estimate the water table depth and then freshwater interface. As I just showed you, the 2D resistivity profiles are effective in identifying fractures. That's also called ERT, or electrical resistivity tomography. Azimuthal resistivity is proven effective in identifying fracture trends. And there's actually a way to estimate fracture porosity from that, which I think I'd like to do this year. So, and then SP surveys were also useful to identify hydraulically active fractures. One of the things that we'll do with the SP surveys is, by the way, we'll set up the electrodes and then I'll pour water on the ground. And you'll be able to actually see the SP change as the water seeps into the ground. It's kind of exciting. So again, we want to kind of build on these results this summer so we can integrate this into eventually a research article. So that is the last slide. Questions?
So one of the things that we will be doing with the geophysics, as you heard, there's a lot of pounding and hammering and stuff like that. So, Phil, you're coming down the week of
The 17th,
the 17th.
17th, that's Saturday, and leaving on the 23rd.
Yeah, and so what we're gonna do is that week that he's down here, some of you will be taking off your other projects and we'll be helping the geophysics group because the geophysics group will be helping you during your week. So we will help each other. So plan on that week. So as Phil mentioned about the clothing, the hats, you guys will be standing there pounding electrodes into the ground, moving electrodes and stuff. So we will help each other out in the project. So even if you're not doing geophysics, you will learn some geophysics. You will be helping out. And I know a lot of geophysics just because I do a lot of the field work. I've actually never really interpreted the results. I just do the physical. So I know all the like logistics of it. I need to actually someday actually process data. Questions?
When you do the test on the location, can you predict other areas? Because it's only a limited space, right? So
Right.
if we're looking at that cenote, I don't know, 7 kilometers away, can you actually predict what is happening in the cenote?
You try to link it together, that's quite a distance, but we try to do that, so.
Is there a pattern that you notice?
Again, we have had problems getting the ground elevation, so that's been our major difficulty. We do think that the pumping well area, the well field, that the pumping wells were affecting the water table. We saw some kind of inconsistent results there the last time.
Yeah, and then the other place that we find really interesting is that Holbox fracture zone. Remember those lines that go up and north and stuff, and I say they discharge right over there? One of the things that we did was that along that field, you don't have those results, do you? There were like two different, you asked about patterns. One of the things wasn't there like two different patterns almost?
Yeah, that's in his poster.
Is that in, yeah, that's in his poster.
Back here.
It's not moving. Where is your mouse at? Oh, there's your mouse.
It's this one.
Yeah.
Okay. There it is. All right. So you can see it right here. So this is one. These two are from Holbox. No, this is from Holbox. No, this one. Could be the well field. We did about 3 of these, 2 in soccer fields up here, and then we did one in the well field also.
Yeah, so there was like this pattern of I guess this one is the soccer, because there was like this and this, so there was like 2 different fracture in there. So one of the things, like Phil said, we look for soccer fields. So when we're looking around for places for you guys to do especially the geophysics, we're going to be driving around looking at the cenotes. You guys are going to be looking for, and Phil will get you up to date on everything you need to look for. We love soccer fields. Soccer fields are great for us because usually they're flatter, all the stuff is removed, and they're in every town. Every town has a soccer field, the kids want to play somewhere. So we usually try to do them in there. So you guys will be looking for places for us to do this in other locations.
So the surveying itself will be like in open spaces like a soccer field?
They'll do the azimuthal surveys, yeah. And we get the other surveys, they need space too, for resistivity. So it's really a challenge to find area. That's what we do so much in the well field. There are roads there.
So we can find roads, soccer fields, things and we don't want a lot of cars driving by, so it's also, soccer fields are nice because they're usually right off of they're not right on the road. We're not doing, because we could do on the road, but.
We don't want to do it on a busy road. So. That's why the well field was good, especially the south Buffalo, because nobody drove down there. I think it was maybe 2 cars the total time for that.
And so we'll look for, like, especially every time I go down there, there is new construction, there's a new area that they've ripped up all the trees, there's something new that goes on. And actually that links into what Jackie's gonna talk about with like urban change and changing. Every time I go down, there's a new place and we're like, oh, wow, great, thank you for giving us this great research area for us to do a project. So before Phil gets there, you guys will be looking for sites, potential sites for doing your research projects, okay?
Okay, I'll turn this recording.
Yep, turn the recording off and then we'll do the one last recording. Any other questions? And the geophysics equipment's already down there, correct?
Yeah,
Put this one here.